question that, well, it might seem obvious, but the answer's incredibly deep. Why doesn't everything just smush together?
Right, why does it matter collapse? It's a fantastic question.
We're going to explore the principle that stops this cosmic smushing, something that governs atoms, stars. It's called the Pauli Exclusion Principle.
Or sometimes the Fermi Exclusion Principle, yeah. And it leads right into Fermi-Dirac statistics.
So our mission today, unpack where this idea came from and just how huge its effects are.
And you've pulled together some great material. It lets us really trace the discovery and see how it fundamentally changed physics.
It really does. It shows how these super abstract ideas have very real consequences.
Definitely.
And like a lot of big science stories, this one starts with a puzzle. Remember the early days of atomic models? Bohr's model was great for hydrogen, one electron.
Simple case, yeah.
But for atoms with more electrons, it just didn't work. It couldn't explain how they arranged themselves or the really complex light patterns, the spectra they gave off.
Right. The spectra were much more detailed than the Bohr model could handle. By the early 1920s, physicists had 3 quantum numbers.
Okay, what were those again?
There was N for the energy level, L for the orbital shape, and L for its orientation in space. These came from sort of refining Bohr's ideas.
So 3 labels for an electron state. But it wasn't the whole picture. There were these nagging problems, things that just didn't fit.
Exactly. Chemists knew for ages that electron shells fill up very specifically. You get 2 electrons in the first shell, then 8, then 18.
The 2, 8, 18 pattern. I remember that from chemistry class.
Right. But why that pattern? The early quantum model had no answer. Why didn't all the electrons just pile into the lowest energy level? It was a big mystery.
Yeah, it's like, why wouldn't they? And then there was the anomalous Zeeman effect. That sounds pretty weird.
It was. So the Zeeman effect is when you put an atom in a magnetic field and its spectral lines split. The normal version was kind of explainable with those 3 quantum numbers, but many atoms showed a much more complicated splitting, the anomalous effect. It strongly hinted that electrons had some other property, something intrinsic, interacting with the magnet.
Something beyond just orbiting the nucleus.
Precisely. It was a clear signal that the electron picture was incomplete.
Okay, so weird filling patterns, weird light splitting. Enter Wolfgang Pauli. He's the key figure here, right?
Absolutely crucial. Pauli was known for being brilliant and incredibly rigorous. He really dug into the experimental data in the early 20s, the spectra, the electron setups, trying to find the underlying rule.
And what did he figure out? What was the missing piece?
His big insight was realizing that to explain everything, especially that anomalous Zeeman effect and the periodic table's structure electrons, needed another property, something he called a two-valuedness not describable classically.
Wow. So not quite spin yet, but he knew there had to be a 4th quantum number.
Exactly. He saw the necessity for it, based purely on the data, even before its physical nature was clear. That's some serious scientific intuition.
And that led him to propose the exclusion principle in 1925, the Ausschließungsprinzip.
Yep, that's the German name. In 25, he laid it out. No 2 electrons in an atom can have the exact same set of values for all 4 quantum numbers.
Like a unique quantum fingerprint for every electron.
That's a great way to think about it. If 2 electrons share the first 3 numbers n, L, ml, they must differ in that 4th one.
And that's where spin comes in.
Right. Later the same year, Uhlenbeck and Goudsmit proposed that electrons have this intrinsic angular momentum, like they're spinning. And crucially, this spin was quantized, only 2 possible orientations.
Well, up or down, basically.
Effectively, yeah. The spin quantum number, m's, could be +12 or -12. That was Pauli's two-valuedness.
And suddenly things started clicking, right? How did this combo Pauli's principle plus spin solve those earlier puzzles?
Oh, it was incredibly successful almost immediately. Take that first electron shell, NO1. For that shell, L has to be 0, and ML also has to be 0. So the first 3 numbers are 1, 0, 0.
Okay.
Pauli's principle says you need a unique set of 4 numbers. So you can have one electron with spin +12, that's 1, 0, 0 + 12, and another with spin -12, that's 1, 0, 0, 0, 12.
2 electrons, exactly matching the observation for the first shell.
Exactly. Boom! It just worked.
That's really elegant. And it wasn't just the first shell, was it?
Not at all. This became the foundation for understanding the entire periodic table, how electrons fill up higher energy levels, different orbital shapes. It all follows from the exclusion principle, the repeating chemical properties. That's a direct consequence.
So the structure of the periodic table isn't just some arbitrary list. It emerges from this quantum rule.
Precisely. It dictates the whole architecture of chemistry, how atoms bond, how substances form, and importantly, it also explained the details of the atomic spectra, including finally making sense of that anomalous Zeeman effect by accounting for spin's interaction with magnetic fields.
Okay, so this principle, born from looking inside atoms, had much wider importance. Which brings us to Fermi-Dirac statistics. How does that connect?
Good transition. Yeah, Pauli's principle was initially about electrons in an atom. But what about systems with tons of identical particles obeying this rule, like all the electrons buzzing around in a metal?
How do they behave as a group?
That's where Enrico Fermi comes in. In 1926, he developed the statistics to describe large groups of identical particles that follow the exclusion principle.
Okay, Fermi-Dirac statistics, what did that involve?
He came up with the Fermi-Dirac distribution function. It basically tells you the probability that a given quantum state is occupied by one of these particles, factoring in that no two can be in the same state.
And Paul Dirac was working on this independently around the same time, too.
Yes, also in 1926, Dirac not only developed the same statistics, but gave it a deeper quantum mechanical basis. He showed it arises from the antisymmetry of the total wave function for identical fermions.
Fermions. Those are the particles that obey the rule, right? Like electrons.
Exactly. Fermions are particles with half-integer spin, like 12, 32, etc. Electrons, protons, neutrons, they're all fermions. And Dirac showed their collective wave function must be antisymmetric.
Antisymmetric. Okay. What does that mean physically? How does it lead to exclusion?
Okay, imagine you have two identical fermions, A and B. The wave function describes their state. Antisymmetry means if you swap A and B, the whole wave function flicks its sign, it gets multiplied by -1.
Okay.
Now, what if A and B were in the exact same quantum state? If you swap them, well, nothing has physically changed, right? They're identical and in the same state.
Right. Swapping them makes no difference.
But the maths of antisymmetry says the wave function must flip sign. The only way something can equal its own negative is if that something is 0.
So the wave function for two identical fermions in the same state has to be 0, meaning that state is impossible.
Precisely. It's a fundamental consequence of their indistinguishability and this antisymmetry requirement. They simply cannot occupy the same quantum state.
That's a really neat explanation, connecting the maths to the physical rule. And you mentioned earlier there's some different terminology floating around. Pauli principle, Fermi principle.
Yeah, good to clarify. Pauli Exclusion Principle usually refers to his original idea about electrons and atoms. Fermi-Dirac statistics is the broader framework for any collection of fermions. Fermions are the particles themselves, half-integer spin. And Fermi Exclusion Principle is often used interchangeably with Pauli's, emphasizing the general rule for any identical fermions.
Got it. Pauli for atoms, Fermi-Dirac for the general statistics, and the deeper why. Okay, let's talk consequences. This seems huge. Stability of matter.
Absolutely fundamental. Without the exclusion principle, what would happen? All electrons in an atom would just collapse into the lowest energy state, the nylon-1 shell.
Atoms would be tiny.
Incredibly tiny. And their electron clouds wouldn't really interact. Matter, as we know it, with volume and structure wouldn't exist. The principle forces electrons into higher shells, creating the atomic structure that gives atoms size and allows them to form molecules.
So the fact that things have size is because of this.
Largely, yes. And it also leads to resistance against compression. Even at absolute 0, it's called degeneracy pressure.
Degeneracy pressure.
Yeah.
How does that work?
Because fermions can't share states, if you try to squeeze them together, you force them into higher and higher energy levels. That takes a lot of force. It's an inherent resistance to being squashed.
So the reason this table feels solid is ultimately quantum mechanics and electron degeneracy pressure.
In essence, yes. It's the Pauli principle at work on a macroscopic scale. And we already touched on how it dictates the periodic table and all of chemistry, electron configurations, valence electrons, bonding. It all flows from this.
Okay, atoms, chemistry, solidity.
What about bigger systems, like metals?
Right, in metals you have this sea of free-moving electrons, but they still obey the exclusion principle. Even at absolute 0, they can't all be in the lowest energy state. They fill up the available energy levels from the bottom up.
Creating the Fermi sea. Exactly. They fill states up to a certain level called the Fermi energy. Think of it like filling seats in a stadium, 1 electron per seat, starting from the front row. The Fermi energy is the energy of the highest occupied seat.
That's a helpful picture. How does this Fermi sea explain metal properties, like conducting electricity?
Well, for an electron to conduct current, it needs to gain a bit of energy from an electric field and move to a slightly higher, unoccupied state. Only the electrons near the top of the Fermi sea, near the Fermi energy, have empty states readily available just above them.
Ah, so the ones deep down in the sea are stuck.
Pretty much. All the nearby states are already filled by other electrons. They can't easily move. So only the electrons near the Fermi energy contribute significantly to electrical current.
That makes sense. What about heat capacity? Why don't electrons in metals contribute much heat capacity?
Same reason, essentially. To absorb heat, particles need to move to higher energy states. But again, for most electrons deep in the Fermi sea, there are no easily accessible empty states nearby. Only the electrons near the Fermi energy can readily absorb thermal energy and jump up.
So most electrons are locked out of contributing to heat capacity at normal temperatures.
Exactly. It explains why the electronic contribution is much lower than classical physics would predict.
Okay, this is wild. From atoms to metals. And you said it even applies in stars. Extreme environment.
Oh, absolutely. Crucial role. Take white dwarf stars, the remnants of stars like our sun. Gravity is trying to crush them flat.
Gross out.
Electron degeneracy pressure. The same resistance to compression we talked about. The electrons are squeezed so tightly that the exclusion principle generates this massive outward pressure, balancing gravity. A white dwarf is basically a giant ball of degenerate electron gas.
Mind blown. A star held up by a quantum rule about electrons not sharing states. What about neutron stars? They're even denser, right?
Even denser. They form when a really massive star collapses, overcoming even electron degeneracy. Protons and electrons get forced together to make neutrons. But neutrons are also fermions. They also have spin 12. So the final collapse is halted by neutron degeneracy pressure. Same principle, different particle. Neutron stars are supported by neutrons resisting being in the same quantum state.
Wow. So electrons in white dwarfs, neutrons in neutron stars. The exclusion principle is the last line of defense against gravity. Does it apply inside the nucleus too? Protons and neutrons.
Yep. Protons and neutrons, nucleons, are both fermions. So within the nucleus, they also occupy distinct energy levels or shells, just like electrons in an atom. This is the basis of the nuclear shell model.
Which explains why some nuclei are more stable than others, magic numbers and all that.
Exactly. Nuclear stability, magic numbers. It connects back to the exclusion principle acting on protons and neutrons in the nucleus.
It really seems to be everywhere for these kinds of particles. But you mentioned not all particles follow this rule. What's the other?
Those are bosons. They have integer spin 0, 1, 2, etc. Think photons, light particles spin 1, gluons, strong force carriers spin 1, the Higgs boson spin 0. Even composite things like helium-4 atoms have an overall integer spin.
And the big difference is they don't care about the exclusion principle.
Correct. Bosons are perfectly happy to share the same quantum state. Any number of identical bosons can pile into the exact same state. They follow different rules called Bose-Einstein statistics.
And that leads to totally different phenomena.
Totally different. Because they can all occupy the lowest energy state, you get things like Bose-Einstein condensates BECs at ultra-low temperatures, where millions of atoms act like one single quantum wave.
I've heard of those. Weird stuff.
Very weird. Lasers work because photons are boson-stimulated emission creates zillions of identical photons in the same state, and superfluidity in helium-4 flowing with zero friction. That's also a consequence of its bosonic nature.
So you have fermions acting all exclusive, leading to structure and stability, and bosons happy to congregate, leading to things like lasers and superfluids. It makes you wonder why. Why this split based on spin? Half integer versus integer.
Now you're asking the deep question. And the answer is one of the coolest results in physics. The spin statistics theorem.
Spin statistics theorem. Okay, sounds important. What does it say?
It provides the fundamental proof connecting a particle's intrinsic spin to its statistical behavior, whether it's a fermion or a boson. It rigorously shows that particles with half-integer spin must be fermions, antisymmetric wave function, obey exclusion, and particles with integer spin must be bosons, symmetric wave function, don't obey exclusion.
No exceptions. It's a hard link.
It's a hard link, derived from fundamental principles.
Okay, remind me about the wave function symmetry again. Antisymmetric for fermions means swapping them flips the sign, leading to exclusion if they're in the same state.
Correct.
What about symmetric for bosons?
Symmetric means if you swap two identical bosons, the wave function stays exactly the same, no sign flip. So if they're in the same state, swapping them changes nothing, and the wave function is perfectly fine, there's no rule preventing them from sharing that state.
Incredible. So this fundamental difference comes down to how the wave function behaves under exchange. But you mentioned proving this theorem needs more than basic quantum mechanics.
That's right. While Pauli could figure out the rule from experiments and Fermi and Dirac developed the statistics, understanding why spin and statistics are linked requires relativistic quantum field theory, QFT.
So you need relativity in the mix, Einstein stuff.
Absolutely. QFT combines quantum mechanics with special relativity. The proof of the spin statistics theorem relies on core principles like Lorentz invariance, laws of physics are the same for everyone moving uniformly, causality, effects can't travel faster than light, and positive energy, particles have positive energy.
Okay, that sounds heavy. How did those principles force this spin statistics connection?
Well, it's pretty mathematical, but the gist is, if you try to build a relativistic quantum theory where half-integer spin particles are bosons, symmetric wave function, or where integer spin particles are fermions, anti-symmetric wave function, you break fundamental rules.
Like what?
Like you might predict faster than light signals, violating causality, or get negative probabilities or other mathematical disasters. The only way to have a consistent theory that respects both quantum mechanics and relativity is for half-integer spin particles to be fermions and integer spin particles to be bosons.
So it's not just a coincidence. It's woven into the fabric of reality as described by our best theories.
Exactly. It's a necessary consequence. The spin statistics theorem takes the Pauli principle from being a brilliant empirical observation to being a deep result of relativistic quantum physics. It shows this rule that structure's matter is profoundly linked to the nature of space, time, and quantum fields.
Wow. Okay, what a journey. We started asking why stuff doesn't collapse, looked at weird atomic spectra, uncovered Pauli's rule, saw how Fermi and Dirac generalized it, explored its role in chemistry, metals, even stars.
White dwarfs, neutron stars.
Yep. Contrasted it with bosons, and ended up finding the deep reason behind it all in the spin statistics theorem, connecting it to relativity itself.
It really is a cornerstone. This principle, exclusion, dictates so much about the universe, from the chair you're sitting on to the stars overhead, and the theorem reveals this non-obvious link between spin and statistics, rooted in fundamental physics.
It's amazing how these abstract quantum rules have such concrete effects. The solidity of things, the light from stars. It makes you wonder, doesn't it? What other hidden rules might be out there, shaping reality in ways we haven't even imagined yet?
That's the perfect thought to end on. There's always more to uncover, often hiding just beneath the surface of what seems familiar.
Absolutely. Well, thanks so much for diving deep with us today. Until next time, keep questioning.